Helo, croeso I sesiwn arall o electroneg gyda fi, Mr Jonathan Williams. Heddi beth byddai'n neud yw siarad am ti mwy o giron. Today I'll be talking about op-amps, operational amplifiers, and what you need to know basically for your exams this year. Right, so where you go. Remember, please, this is a live event. You can watch it again on YouTube. And when you're watching on YouTube, what you can do is you can pause and you can look at my calculations. You can use a calculator to try and work out the things. Remember, using a calculator in an examination technique is really important. Right, we start basically with the equations that you will need for operational amplifiers. So in your data sheets, if you have a look, you will have these equations. So the first one there, that is for a non-inverting and an inverting amplifier. All right, so the G stands for the gain, V out and V in for both of them. The next one, the 1 plus, this will be your non-inverting. So maybe in an exam, just put down the non next door to it. The one underneath it, okay, is the gain for a inverting. That minus sign is the giveaway, so that's your inverting. The one underneath that is for a summing amplifier. Okay, so remember, amplifiers in Welsh, mwy o diron. So mae gyda ni non-inverting, mae gyda ni yr un sydd ddim yn gwrthdraddol, inverting yw gwrthdraddol. For that section there, that refers basically to your saturation, dirlawnder. All right, so for a V out, the VS, so your supply voltage which you're using for the op-amp, if your positive is bigger than your negative, then it goes into positive saturation. And if your negative is bigger than your positive, it goes into negative saturation. V out for a V in refers to a voltage follower. Basically, an op-amp which has no resistors, it just has a gain of 1, and it's used to transfer voltage from one place to another place. Slew rate, okay, that refers to all op-amps. It's a characteristic where if you put in a voltage, you will basically end up with a signal which isn't exactly the same because it takes a time delay, right? And we have another slew rate equation as well. Okay, so away we go with some calculations and looking at some circuits. So first thing, basics of op-amps is please remember that with an op-amp, how it works, what you basically have are two terminals. So those two terminals, you have the positive and you have the negative. If positive is bigger than negative, again, like now, you're in positive saturation, you've got 9 volts. If the input of the positive goes below, okay, as it's done now, you've now gone into negative saturation. Okay, so it's gone into the -9. Positive is bigger than negative, goes into positive saturation. Negative, if it's bigger than positive, goes into negative saturation. So that's the basics of how an op-amp works. Okay, things that you have to learn for an exam. They will ask you about the characteristics, or name 2 or 3 characteristics of an op-amp. Okay, so mae rai bod chi'n gwybod beth yw nodweddion o mwyadur. Right, so first thing you remember, it's got an input impedance of infinity. Output impedance is 0, slew rate is infinite, and a CMR of infinite. Open loop gain is infinite as well. Okay, so characteristics, nodweddion o mwyadur. Please, 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 mae just rhaid I chi dysgu'r hynna off top eich pen. Okay. Okay, and we go to the first op-amp today, which is a non-inverting. Non-inverting because the input voltage, but voltage ddim yn mewn i'r un sydd ddim yn gwrthdroi fe. Okay, positive. 2 resistors, top resistor is always called the feedback resistor, and the other resistor is always called V1, R1 as well. Right, things that you have to remember with these graphs. So this is the characteristic of a non-inverting, and saturation values are so and so. Okay, please remember how to work this point there out. Comes up time and time again. So at that particular point, it causes saturation. So what you've got is for both op-amps, gain is your V out over your V in. So if you rearrange that, V in would be V out over gain. So from there, it is possible to work out that V in would be the voltage which causes you to saturate. So look to see that VO there is your saturation voltage. So from the graph, where it flat lines, that's your saturation. Look to see what your gain is, and that will give you the voltage which will cause saturation. All right? So voltage bydd yn achosi dirlawnder, defnyddio'r rhafaliad o gyfer gweithio fy mas. So, beth sydd gyda ni fan hyn yw ymwyadur sydd ddim yn gwrthdroi. It's non-inverting. So let's look at what happens. Just remind you of the workings. Voltage changes. So you get a gain depending on your feedback resistor and your input resistor. Okay, and what's happened there now? Voltage has got so big that it's now gone into saturation. Okay, bring it back down. And the voltage will decrease. But there's a gain. Okay, mae gyda chi cynnydd yn y voltage sy'n dod mas I gymharu gyda'r voltage sy'n dod mewn. So that's the basics of a non-inverting in angwrthdroiadol. What you can do with these as well, that was a DC signal. I'm going to put in an AC signal. Okay, so we're going to roi mewn current eiledol. What you can see here, the blue one which is coming in is the small voltage coming in. And then the red one shows the output voltage, which has got gain on it. So non-inverting, so positive will give you positive. And this one shows clipping distortion. Right? So it's a distorted signal because what the op-amp is trying to do is give an output greater than its saturation, but it can't. Right? So it will blow up. Right, so a op-amp will only give its maximum voltage, which happens to be its saturation level. So please be aware of that. So in this case, yeah, we've got clipping distortion. It can't give more than the saturation level. Okay, on to an example or two of what they could ask you in an exam. So first one, it's asking you, use the graph to determine saturation voltage. Nice easy one. Okay, saturation voltage is there. Okay, and the top bit is there. So if you use the graph, show the examiner that you're using the graph, put those dotted lines in. Remember, we've got a plus and a minus value. So in this case, we've got plus and minus, and we've got 16 volts. The voltage gain, so the gain in this case, the easiest way to write it, to work it out. So the gain would be the V output divided by the V input. So your output voltage, you can take any part, 16 volts, down any part of the linear part of the graph. Okay, but it's easier basically just to take the saturation where it happens. So I've got 16 volts on saturation, and the place where it happens, okay, I would look at 210. Positive or if it's minus, okay. So in this case, you've got 210, and watch the units, you've got millivolts. Okay, so that would be times 10 to the minus 3. Okay, so if you put that into a calculator, you will end up with a gain of 76.2. Now remember, in this one, it is a positive non-inverting. So negative gives you a negative, positive gives you a positive, right? So it is just 76.2. You could use any other part of the graph. For example, you could use that point. Okay, so you'd use the 10 volts and look to see what the input value is. Okay, and you could use those values as well if you wanted to. Okay, how to wire up. They will ask you very often to finish a diagram for an operational amplifier. So you just have to memorize basically the non-inverting and the inverting. Okay, so this time we've got a gain of 80. So I know it's a non-inverting. So the first thing I'm going to do is put in my feedback resistor. Okay, next thing is you know it's a non-inverting. So that is going to go straight into your inverting. Then what you've got to remember is you have a resistor which goes to ground. Okay, and there is a link. That is your feedback resistor. Okay, and there's your R1, which is coming in. Choose suitable values, which will give you a gain of 80. Right, first thing, because it's a non-inverting, my gain, look up your equation. So you got your 1 plus your RF over your R1. Okay, so in this case, I want a gain of 80. So let's put the numbers in, substitute in. And then, if you notice, you will always tend to have two resistors and you don't know a value for either of them. So the rule is you will always choose your input resistor or your R1 to be 10K. Okay, so always choose that one to be 10K or more. Doesn't matter. 10K tends to be the value we tend to use. So what we've got is RF. Okay, and that is divided by the 10K. So just rearrange that, take the 1 over. So you've got 79. Okay, and then 10K will come up. Okay, which will give you 79K. 790K, sorry. Okay. So yeah, if you have two unknown resistors, choose one to be 10K. Right, and here we go. Maximum output voltage that avoids clipping distortion. Okay, so we'll go with a gain, which is V out over V in. So I'm asking what output voltage of the microphone, which is the input voltage of the op-amp. So I'm going to need that V in. So if I need that V in, just substitute, gain goes down, cross multiplication, V in comes out, the gain comes down. Okay, and in this case, the saturation voltage was 16. So if we do the 16 and the gain is 80, okay, this will give me 0.2 volts. So that's the voltage which will cause the saturation to happen. Okay, they were like giving you graphs, and from those graphs that you have to draw a new graph, what comes out. What I like doing with these is picking points. So in this case, if the output is 0 to start, and put a little dot in or a cross in, then what I'm going to do is I'm going to work out what the voltage would be for these peaks. There, and there. Okay, so the first one, what I've got is I've got 150 millivolts there. Notice the scale. So if I've got 150 millivolts and the gain was 80, then 150 millivolts times 80, that'll give me 12 volts. Now this one is a minus 150, so that'll give me minus 12 volts. The peak here is 200, so if I take the 200 millivolts and I multiply that by 80, that's going to give me 16 volts, which happens to be saturation in this case. There's my 16 minus 16. So if I just pick these points, minus 12, okay, I'm just going to sketch that in. Minus 12 will go down to the minus 12. And 16 volts corresponds there, and I've got minus 16 corresponding to there. So what I'll do now is simply sketch the same shape. Okay, there's no need to worry about clipping distortion in this case because 16 volts was saturation and I'm not going bigger than saturation itself. Right, this is the non-inverting. Notice again, right, you will have to learn that diagram. So notice this time that the positive goes down to ground, there's no resistor there, and your input resistor goes into the negative terminal with the RF in the same position. If they ask you what is the input impedance or the input resistance, so they tend to ask input impedance of a non-inverting amplifier, it will be the value of that Rn. Okay, I'll just flick back a couple of slides. If they ask you what is the input impedance of a non-inverting, there's no resistor there, so that would be infinite, or I would say it is very large. Okay, so it's one of those characteristics you have to remember. Okay, so with a non-inverting, notice the characteristic. So if you've got a negative voltage, you've got a positive output. Okay, so the shape of the graph is basically a mirror image of the other one. Same thing they could do again. They could ask you to work out that point which is there. So that point there would be V in, would be the V out, which is just saturation level again, divided by the gain. Okay, that is so handy to work out that point where saturation happens. I'm going to look at the graphs which these cause. Biggest thing in this one is that if your input voltage is positive, notice this is negative. Okay, so when you're doing graphs, make sure, yeah, you're going negative if you've got a positive, and if you've got a negative, you'll be going positive. If they are inverted. So in this case, yeah, we've hit saturation at that point again. Input voltage is positive, but my output voltage is negative. Okay, and same thing if it comes to a AC. Okay, there we go. Blue one is the one, small one coming in. Notice the red one, which is the negative, is inverted. So it's a negative graph. Okay, changing the resistance value of the feedback resistor here, so a much larger gain. And then we've got clipping happening again. Okay, so clipping distortion, they could ask you, how do you avoid clipping distortion? So you could avoid clipping basically by making the gain smaller, the G smaller. You could also use a V in, which is smaller. Okay, how can you avoid it in design? What you could do is you can make your feedback resistor smaller, which will give you a smaller gain. So a ways to avoid it. Okay, that is a handy one. They've asked that in exams a few times. Okay, so looking at a graph that they could ask you to draw here. So in this particular case, what we've got is a gain of minus 75. Okay, draw the transfer characteristics. So first thing, they've got an input voltage between plus and minus 300. So I'm looking for a threshold again. All right. So the threshold will be, I take the threshold. Okay, it's my saturation level, which is the V out bit. Okay, and it's divided by the gain. Okay, my gain this time is minus 75. Right, so my V out, okay, saturation can't get bigger than 18. If I take that minus 18 divided by the minus 75, this will give me 0.24 volts, and it's a minus, okay? So what I've got is minus 24 volts. Well, basically, sorry, so that'll be 240 millivolts. So I'm looking at a point on a graph, which is and I'm looking for a voltage over there. Right, so it's a minus 75. So this means it's an inverting. So if I am negative voltage in this area, it's going to give me a positive. So positive will be 18. So I'm looking at 15, 16, 17, 18. I'll put it across in there, and I'll be on minus 18 on the positive value. Down there. So that shows the saturation. Now, and if you've done this right, when you join those points up, you will always go through the 0, 0. Okay, so that's your characteristic, okay, of an inverting. Right, third type of op-amp is your comparator. Right, these are really, really useful amplifiers, operational amplifiers. We're ironically adeiladu. Okay, a cymharydd. So mae gyda'r cymharydd, mae gyda chi voltedd yn mynd mewn ar y positif a'r negatif. A beth mae'n neud, mae'n cymharu. It compares whatever you have on the negative and the positive. So if positive is bigger than negative, you will have a positive output. If negative is bigger than the positive, you will have negative. Okay, let's have a look at this in action. So in this particular simulation, we've got a light-dependent resistor on the top here. So the light level is going to change. And if that light level changes, you can see the probe at the minute is rising on the red. So that's the light level, and it's past the threshold value. So at that particular point, positive became bigger than the negative. Okay, and we've got a voltage now decreasing. That's went into negative saturation. Now in this case, look, I've put in a negative saturation value of 0. It is possible, right? You don't have to have a negative voltage always put in as the saturation levels. Ar dy lawnder, sy'n rhaid I chi cael 0 volt, negatif, chi'n gallu rhoi 0 mewn, sy'n meddwl bydd yr allbwn ar 0 os mae negatif yn fwy na beth yw'r positif. So that's the basics there of a comparator. Normally on the comparators, you will have a sensor. So in this case, there's the sensors, there's light-dependent resistor, which means the voltage at that point will change depending on light. Now notice there, okay, that's called the fixed threshold value. So what I've done, or what they do is I have two resistors, 1 and 2, they're fixed, right? And those fixed resistors will keep that voltage there at an exact point. Now in this case, I've got two resistors, 10Ks, okay, they're exactly the same. So if they're exactly the same, they will have the voltage of the supply. So that point there is fixed at 4.5, right? You can change it if you wanted, put a variable resistor in, if you wanted to change the threshold values. Okay, and this is what I've got here, is comparator. So mae gyda fi'r cymharedd, right? So by changing that threshold value, so I've changed it. Now, light level, which will cause it to flip, change your outputs, is now different. Pretty cool. Okay, changing that threshold value there again. So that light level, I can change it. Okay, so as you can see there, that bit there is now different to what caused it at the start there. Right, so with these comparators, again, you will have to draw it. Sometimes they will ask you to, maybe they'll give you the opamp itself, but yn rhoi'r mwyafrif i chi, a wedyn maen nhw'n gweithio chi I addo y gwrthydd mewn bydd yn galluogi chi falle I adeiladu y cymharedd. So they'll ask you to put in the resistors, draw the resistors in, which will let you finish completing to make a comparator. Okay, so here is an example of one. All right. There'll be more on this tomorrow when I do about transistors. Okay, and this is in lesson 4. If you're watching on YouTube, we can have a look at it. I'll do more about potential dividers, which will come into play. But often you will have to work out a voltage basically at a certain point. So I'll just put this in now. So voltage at that point. So you've got to basically have two resistors which are working as a potential divider. Okay, gwahaniaeth potential. Felly beth byddwch chi'n neud if you wanted to work out the voltage at that point? It's the supply voltage times the bottom resistor, and then R1 plus R2. Okay, this is a classic one, which is not given in your data sheets, right? You need to learn that one and use it. So whenever you have two resistors, it's the quick way of working out what's the voltage across a certain resistor without having to work out currents or anything like that. Yeah, let's go and try and use it. Here we go. So it says use the graph. So examiners want to see basically lines being put on the graph itself. And it wants to determine the resistance of the thermistor at 25 degrees. So if I go for 25 degrees, temperature's on the bottom. Okay, and read that off on a graph, which I've done already. Okay, that would give me a 5k. So I'm using basically the graph in order to work that one out. So if I wanted to work out what the value of that one be, so now flicking back, I know that that is 5k. So what I can do now, I can use those two together by using potential divider, defnyddio'r gwahaniaeth potential I gweithio mas beth bydd y voltedd o'r gwylod. Felly beth byddwn ni'n neud? The supply voltage was 12 volts. Okay, it's there. So as we need 12, llosi hwnna gyda 5k. It's the bottom resistor. I've got 10k and a 5k. Okay, as we gweithio hwnna mas, that gives me 4 volts. Okay, so what I've got there was a 5k on the bottom, 10k resistor is the top. That's where those two values come from. So what type, if I got 4 volts and it's asking me now what voltage or what resistance should that be? So my threshold is 4 volts. So I have to basically create this point there. That point there. Point has to be 4 volts. Okay, so looking at it, I've got a 4 volts across this bottom resistor. So that means looking at supply, I've got to have 8 volts across the top one because those two have to add up. All right, so I've got to have twice the amount of the voltage on the top than I have on the bottom. So the easy way to do that, if it's going to be twice the voltage, it's going to be twice as big in terms of a resistor. Dwywaith mor gymaint ar gwrthedd, mae dwywaith mor gymaint o voltage gyda fi. Right, so if the 15k is on the bottom, twice as big, that would be 30k. Okay, there's a reasoning. It's basically 2 times the 15k for the top one. Okay. Water is changed temperature and reference to VT and explain how Vout changes when the temperature increases from 20 to 25. Right. First thing is that the reference voltage, which is the negative, is fixed. Right. So that is stuck basically at 4 volts. So that's the first thing I would say is Vx is constant. And it is fixed at, again, it was fixed at 4 volts. Right, now then, thing is you have to know about a thermistor is this characteristic. So with a thermistor, as the temperature in degrees centigrade increases, the resistance of the thermistor decreases. So if it's on 20 degrees, we would have basically a bigger resistance. So if it's got a bigger resistance, the voltage, okay, which is at T, will be bigger because there's more resistance. When you think about it, V equals IR. That is a bigger resistor, and that will be bigger as well. So VT will be greater. Okay, so as it goes from 20 to 25, so this is at 20 degrees, VT will be greater. Then as it gets closer to 25, so VT will decrease. Okay, put an arrow showing decrease sign. So it decreases because it's getting warmer. Okay, so as it gets warmer, resistance decreases, so the voltage goes down. So eventually, when it reaches a 25, it'll switch itself off, okay, because it's reached that temperature. Okay, going on to another setup. Right, these are called summing amplifiers. Okay, so gyda mwy o diron sydd yn adio, you will have more than one input, okay, and it's connected to the inverting. Right, so more than one. Equation is given. Okay, mae'r afaliad na gyda chi ar blaen eich papur and eich data sheet. Right, if you have a quick look, I'll need pip fach ar mor hyn yn gweithio. So, in this case, I've got 2 volts going into each one of these channels. So if I close the first channel, it gives me that output. Second channel gives me that one, and the third channel gives me smaller. right? I've got different resistors on each one. Right, so what I do now, if 3 switches are closed, you can see the output got bigger. When I open those switches, the output gets smaller. So the combination of the switches will give me the output itself. So instead of having just one switch, one output, combination then basically becomes the output. Now, for those who are studying A level, as in the second year, these are the basics for turning a digital signal into an analog. So these are DACs, okay? Digital to analog converters, right? Also the summing amplifier. So very useful. Right, example of how we use it. Right, so in this case, we've got two volts. Okay, in this one, we've got 1.8 volts going in on T. So first thing, always in an exam, okay, you might get a mark for it. Your V output, quarter equation. So you've got the minus RF, and then you've got your bracket, which is V1 over R1, and your V2 over R2. We've only got 2 resistors, so I'll leave it there. Okay, so a simple case of putting the numbers in, but make sure you got the right ones. Minus feedback resistor is the top resistor, 40k. So your V1 resistor R1, so your voltage is 2 and resistor is 20k. And your second one, voltage, you've got 1.8 and your resistor is 10k. Okay, I'm going to pause there. If you're on watching it, work it out. Okay, that is definitely one that you need to practice basically on your calculator. All right, by putting all of that into, by using the fraction buttons, what you will get is 11.2, but it's a minus value, volts. Right, that minus because it's going into the inverting terminal, so it's an inverting amplifier. Summing amplifiers are. Okay, here we go with another graph on what they can do. So as I mentioned before, what I would like to do is basically work out what the voltage values are at important points. Okay, so I've got a voltage value at that point and work it out there and work it out there. So in this case, it says that one of them has been kept on 2 volts, but the T signal is replaced by this varying signals. Okay, so what I will do at the 0 volts there, yeah, I will put a little equation next door to that one if I wanted to. Don't be afraid to write on the paper itself. So what I have would be the V out there would be, okay, minus 40k, brackets. Okay, and what I have is a constant 2 volts over 20k. What was coming in was 0 volts at this point. So I'll put in 0. So over the 10k. So at that particular point, if you work that out, that voltage at that point, okay, would give minus 4. Now, if I do the same, so at this particular point, okay, V out there, if I do the same thing with the equation, set it up, minus 40 would be 2 over 20, and then it would be plus 1 over 10k. Okay, if I do that calculation, then at that particular point, I would end up with minus 8 volts. Okay, that's something that you could try. All right, at this particular point, I substitute in the values at that one, and that would give me 0 volts at that point by using 2 volts over 20 plus minus 1 over 10k. If I put those points in on the graph, so the crucial points in the graph be there, that's minus 8. Okay, that point and that point are the same because they're on the zeros, and then next point is on 0. Okay, and so on. So if I complete the graph, okay, and I could do it for the rest of it as well. Right? So crucially, if you have graphs, look for, you can't do it for every point. So look for certain points on that graph that you think, right, I'm going to work out the value for that by using this equation and then put that cross in. Okay, it will always help you. Right, another feature of op-amps is that op-amps will give you a gain, right? But if you're using AC, there comes a point where your op-amp is not capable of giving you that gain anymore. The frequency has become so big, basically your op-amp doesn't cope. Okay? So, mae gyda chi yr amledd special lle mae'r fowtedd wedi cwmpo 70%. The frequency will cause your gain to drop to a point where it reaches 70%. So that area where it reaches that 70% is called the bandwidth, a lled band. So lled band yw 70% o beth dyle fe fod. It is 70% of what it should be. Okay? So no op-amp will ever give you an infinite bandwidth, right? Bandwidth is the frequencies over which it can work and give you the gain it wants, but then starts to drop off. Once past 70%, it's useless, okay? So op-amps will always be used with frequencies where they give 70% or more of what they should, okay? So 70% is really, really crucial. Okay, so here's an example for one. And all op-amps have something called a gain bandwidth product, right? It'll be quoted in a data sheet or in a table. So I'll come back to this one. Got an example here of a data sheet for an op-amp. So you've got this thing called the gain bandwidth product, right? So when they're made, they test them and they will tell you. So gain times the bandwidth will give you 3.6 megahertz. So I'll come back on this one. You've got a voltage amplifier designed to give you -75 and gives you a gain bandwidth product of 3.6 and it saturates at 18 volts. So calculate the bandwidth. So gain multiplied by the bandwidth will give you 3.6 megahertz. So 3.6 times 10 to the power of 6. So if you substitute in the gain to work out the bandwidth, so that gain will now be 75. I know it's set minus. There's no need to put the minus in. You can if you want to. If you did, it will give you minus value for bandwidth, which is impossible. Okay, bandwidth is always a positive number. Right? So if you rearranged for that, the bandwidth would be 3.6 times 10 to the 6, and then it would divide it by the 75. That will give you 48,000 hertz, okay, or 48 kilohertz. All right. The gain is -75. Now notice there's no minus value on here. Characteristics, bandwidth for amplifiers, they always have a voltage gain. It's never negative, it's always a positive. So I'm going to go 75, so the 75 will be about there. So a point I know is that 48 kilohertz, so 48 kilohertz will be there, it will be 70% of what it should be. So it should be 75. So if I take that 75, multiplied by 70%, the easiest way to do it is just multiply by 0.7. Okay, that would give me 52.5. So I know at this particular point, I'm going to go down to 52.5, okay, which is going to be roughly about there. Looking at it. Right, so now what you've got is the characteristic. So it'll give you the voltage. Now, it doesn't matter where you start dropping. I'm going to start dropping there and tails off. All right, so a graph like that would be fine. Okay, what I'll do is just delete that one. Now, it wouldn't be wrong if you did this and it sort of fell later, okay? That would be a better op amp, okay? Because it's able to keep its gain for a longer time. So anything where you start dropping it down, they're looking for basically you're hitting the 70%. Okay. This is a -60, and it asks you to complete the diagram. I'm just going to do this one quickly. So there's your feedback resistor, and there's your input. Because it's the minus, goes into the input, bang. Okay. And it says a variable voltage gain. So it is possible for you to get a variable gain by using that resistor, which is there. Right. Often, two resistance values, again, they're asking you to work out the values which will give you the -60. So it's an inverting. So in inverting, you have minus RF over the R1. So the minus RF in this case, now one, don't know both of them. So what did I say before? Choose one of them to be 10K. Okay, so I'm going to put in 10K as my input resistance, which is on the bottom. Okay, take the 10K up. Okay, and that will give me 600. Okay. Ohms. Okay, now in this case, it's asking us what's the input impedance of this voltage amplifier. So that one is my input impedance. So if I chose 10K, that is 10K. Okay, and here we go again. It's asking us basically to find out measured to be what's the input voltage, what's the new voltage gain. So in this case, gain will be voltage in output over voltage in. Okay, so the new output voltage is -9. I'm going to have 200 millivolts in. Okay, and that will give me a gain of -45. Minus because it's an inverting. New maximum bandwidth. Okay, so gain multiplied by the bandwidth. Okay, and will give me 3.6 megahertz. So what I'm going to do now is work out the bandwidth. Gain goes underneath. Gain was, or is 30. Put in the -30, as I said, there's no need for it. So bandwidth from there becomes 120 kilohertz. One thing maybe you should realize is because gain times bandwidth is a number, right? So I'll put that number in. It's what they quote on a data sheet. So in this case, it was 10 megahertz. It's worth remembering, if your gain goes bigger, your bandwidth will always decrease. And if your bandwidth increases, then your gain will decrease. So it's a compromise that you have with op amps. So they could ask you that. So what happens if the gain increases? What will happen? Explain. What will happen to your bandwidth? It will decrease. Okay, and the way you back it up is by using your equation. Okay, and finally is this thing called slew rate. All right, now slew rates, basically what an op amp will do. And so in this case, what we've got is an input voltage. Right? So this is being put into the op amp itself. Now op amps, ideally, if it was ideal and had an infinite amount of slew rate, now in this case, it's going to give me a saturation level of 13. So if I put 10 volts in and the gain was -30, okay, it's going to try and give me a huge output voltage, but it can't go bigger than 13. So if it's ideal, it's an inverter as well. What it would try to do, if it's ideal, would be it would give me drop straight away to -13, keep it, okay, and then drop it. So this would be an ideal op amp, right? But op-amps are not ideal because they have this thing called a slew rate. So they can't cope basically with giving you, an instantaneous change like that. So in this particular question, the slew rate, if I flick back, okay, the slew rate was 4.8 volts every microsecond. So you can only change 4.8 volts in every microsecond, right? So in this case, it would be trying to change my slew rate equation. You have, if you look in your data sheet, your slew rate is the change in voltage, and which is the trend change, okay, divided by the time it takes for it to do. Now in this case, it would be trying to change itself 13 volts, okay? Got 10 volts going in, gain is 30, it would be trying to give you 300 volts, can't, gives you your saturation. So it's going to try and change 13 volts. Now it's basically, that will take it, what's the slew rate in terms of time? It was 4.8 volts per microsecond. So that will give you 2.7 microseconds. So what I'm going to do from that point, remember it's a negative, it's an inverter. So what it's going to do, it's going to take 2.7 microseconds. So I'm going to go to change. So that'll give you 2 seconds. Okay, and 0.7, and then corresponds to the minus 13, should be down there. Okay, and then what you've got, that particular point, is going to try and change down from the 9, but it's going to take another 2.7 microseconds to change. So that 2.7 will bring you to there. Okay, so if I draw it in, that shows what an op-amp would do if it were to give it a step voltage. Okay, that shows you the slew rate, that change, because you can't keep up. Okay, so hopefully that's helped you a little bit with your revision, basically, on op-amps. Gobeithio bod hwnna'n helpu chi gyda bach o mwy o diron. So now question 3. If you go back on YouTube, and if you go on the Carlam website, you will see pre-recorded videos which we've done before. Lesson 1 was on logic, lesson 2 was on timing. So this is the third one. So the next one, which is on tomorrow, will be on transistors. Okay, thank you for watching.